In this video, we're going to look at the corollary of the equivalence class theorem. But before we can state the corollary, we need a new definition. And we're going to let S be a set. We're also going to let F be a collection of AX's where X is pulled from an indexing set I, be a family of subsets of S. We call this family of subsets, F, a partition of the set S if and only if two properties hold. The first property is that S is going to be the union of all of the A sub x's. And the second property that we're going to need is that for x and y pulled from my indexing set, AX and AY will either be exactly the same set or AX intersected with AY will be empty. In other words, we might have duplicates in our collection of family of subsets, but we're not going to have subsets that overlap each other if they're not equal to each other. We can draw a picture of what a partition looks like. The basic idea behind the definition of a partition is that if this is my big set S, then we chop it up into a bunch of pieces. And because this is finite, I'm going to label these pieces. And the pieces would have to be disjoint. So AI intersect AJ here would be empty if I is not equal to J. And this would be a particular picture of a finite partition. But that gives you an idea of how a partition works. Well, let's now look at recalling what the statement of the equivalence class theorem is. So I want to recall the equivalence class theorem. And the equivalence class theorem says the following. If we let tilde be an equivalence relation, on set S, and we pick A and B inside set S, then we know that the equivalence class containing A and the equivalence class containing B are either one and the same thing, or the equivalence class containing A intersected with the equivalence class containing B is equal to the empty set. In other words, two equivalence classes are either exactly the same or they're disjoint. And what I want to point out is that this property here is the second property of set partitions. So what we have now is an idea that we can formulate as a corollary to the equivalence class theorem. So I want to go to the next page to state this particular corollary. So our corollary is going to say the following. Let's let tilde be an equivalence class, an equivalence relation on set S. Then the equivalence classes for tilde form a partition of set S. In other words, First of all, S is going to be the union over all of its equivalence classes, which can be written as the union of the equivalence class of A as A runs through all of S. And the second thing is that two equivalence classes are the same or they are disjoint for all A and B's pulled from set S. Now, one thing that I kind of want to point out is that set S here is both the set that we are partitioning and it is the indexing set. The other thing that I want to point out is that we already know this part from the equivalence class theorem. So the only thing that we actually have to prove is the fact that S is the union of all of the equivalence classes for tilde. So let's put this into yet a different kind of color. This here is what we have to prove. So we still need to prove this. So the proof of our corollary is going to start with the observation that the boxed-in stuff is already known to us. Technically, that should be labeled as property 2. And then we're going to be left with proving property 1. So let's look at how we're going to prove this corollary. So the proof of the corollary. We're going to start off with the fact that we already know. Let's actually go ahead and say that as we already know, so let's erase that. We already know that if A and B are inside S, the equivalence classes are either exactly the same or they are disjoint. So the family of equivalence classes already satisfies property 2 of the definition of partition. Hence, all we need to do is show that S is indeed the union of all of the equivalence classes. But it turns out that's not very hard to prove. We're going to do a double inclusion proof. So we will use a double inclusion proof. And the first thing that I want to do is I want to observe that since each one of these guys is a subset of S for all of the A's inside S, we do know for sure that this union has to be a subset of S. If you union up a bunch of subsets, you can't get outside of the set that they're all subsets of. So now all we have to do is prove that the inclusion goes the other way. So all we need do is show that S is a subset of this union. Well, let's see, how are we going to do that? Well, we're going to let little x be any old element of S. And we already know that x does belong to the equivalence class containing X. And the equivalence class containing X is going to be a subset of the union of all of the equivalence classes, because it's one of these guys. This guy here is one of the sets in the union. Well, what does that mean? So what we now have is X is inside this set, and that is a subset of this. And I need to erase that. Get my notation right. Hence, X inside set S implies X is inside the union, and that's enough to imply that S is a subset of the union of all of these equivalence classes. And because of that, we can conclude that S is indeed equal to the union of all of the equivalence classes, and we already know that the equivalence classes either overlap completely or they are disjoint for all A and B inside set S, and hence these last two things say the family of equivalence classes is indeed a partition of set S, and that completes the proof.